Hello, we are looking at the free response problems in the recent 5 years. And let's look at 2019 free response question number 3. This is a combination of precipitation reactions and buffered solutions. And similar precipitation reactions are found in 2022, 2023 free response questions also. Important topic to understand. And let's work on this problem. First, let's look at the problem. Sodium carbonate. This one is a salt. So we can have this sodium carbonate from our chemical shelf and prepare a solution. And we have also calcium nitrate solution. Let's go to the chemical shelf, take out calcium nitrate and prepare 1.0 molarity. So then problem says this is excess amount and 1.0 molarity of sodium nitrate. And we have 50 ml of sodium carbonate solutions. So this one is a limiting reactant because calcium nitrate is an excess amount, then automatically the other reactant, which is sodium carbonate, becomes a limiting reactant. So this is an important topic, limiting reactant and excess reagent, excess reactant. The problem clearly states that calcium nitrate is an excess amount and it is indicating that the other reactant is limiting. And it is forming sodium nitrate and calcium carbonate. Here I wrote calcium carbonate in red color, red font, showing that the state solid. So this is a precipitation reaction because the solid formed and it is an insoluble. Let me erase it. It is, let me erase this one. This is insoluble solid precipitate. Okay, so this type of reaction we call precipitation reaction, and it is asking us to write the net ionic equation for the reaction above. So typically we want to know, like when we mix two clear solutions, we see immediate formation of a cloudy solution. And as we see the cloudy solution on a table of the lab, we see within 10 minutes or 20 minutes of time, then the solid pressure, the cloudiness comes down, settle down to the bottom of the glassware, forming, the heavier, it shows heavy particles, solid particles. And how can you write, we want to know why this result is forming and by writing a net ionic equation. So important concepts to remember, then the state is important. The aqueous chemical species, especially salt, when the state is aqueous, meaning this is homogeneous solution, and it is completely dissociated. It is present as completely dissociated. So aqueous meaning it is already soluble. So this one is already shown in the state of aqueous state, meaning it is always soluble. But the solid, then we can see by our eyes it becomes cloudy, meaning at least the size of the particles becoming micrometer. You know, our visual range of light, the light wavelength is in between 400 nanometers to 700 nanometers, which is sub micrometer range. So the size smaller than those ranges we cannot see. When you see something like dirt, something like cloudiness is there, meaning that those particle size at least micrometer and above, means because the size of an atom is nanometer, sub-nanometer size, it means millions of those ions are sticking together forming insoluble ionic compound. So then they are actually present as cations and anions, like sticking together like magnets. So we cannot dissociate them. The actual state is solid and insoluble solid precipitate. Polyatomic ions usually do not dissociate. So sulfate, nitrate, in this case, again, carbonate, do not break them apart and write it as it is. And spectator ions, they do not participate in chemical reactions. They are just part of a physical change. Initially, they were in small amount of solution. When we mix them together, they are now present in large amount of solution, but still their chemical identity does not change. So it is a spectator ion. So let's first write it complete ionic equation. Complete ionic equation. So break apart every aqueous solution. Na2SO3. So Na2, it contains 2 of the sodium cation per formula. So from formula, 1 mole, 2 of sodium cations coming out. It is all aqueous. And CO3 carbonate is 2 negative charge, and it is mixed with the calcium 2 plus cation and mixed with 2 of nitrate anion. It contains CnO3 2 and then 2 NO3, and it is forming 2 of sodium. In this case, we need to distribute 2 of sodium, 2 of nitrate. So 2 of sodium cation and 2 moles, especially 2 moles of nitrate anion, and forming CaCO3. CaCO3 do not break apart. Okay, let me emphasize this one more time. So when we have I need to correct the state. This one is solid. Okay, so when the solid insoluble solid precipitate, their actual state is solid. These cations and anions binding together. Now let's compare left hand side, right hand side, and let's eliminate spectator ions. Sodium cation doesn't change. 2 moles of sodium cation going into the chemical reaction. 2 moles of sodium cation still available. 2 moles of nitrate ion still available. So spectator ions, these are spectator ions. They do not change in this chemical reaction. Now, initially, calcium cations and carbonate ions, they are free ions surrounded by water molecules, hydrated, individually distributed, but after we mixing them together, they are sticking together, and multiple millions of them sticking together with each other, positive, negative, this way, and forming insoluble solid precipitate. So this is net ionic equation. So net ionic equation is calcium cation 1 mole, initially free one, and carbonate anion. It is binding together to form calcium carbonate and solid. So this one is net ionic equation. Important concept in understanding especially precipitation reactions and acid-base neutralization reactions. Now let's see how to understand this one. The diagram below is incomplete. Show the major ionic species present. Remember, this reaction we have a spectator ions. Spectator ions is sodium cations and nitrate anions. Not only that, we have excess reagent, which is calcium NO3 2, means we have in solution we have calcium cations and nitrate ions also in amount, excess amount. Here now we see 2 of, let me circle it. We have nitrate and sodium, and nitrate sodium. So we have nitrate sodium comes these spectator ions. Now the other remaining 2, we have those nitrate ions right there, nitrate ions. But the cation is missing, so we need to draw the cations. The cations must be calcium 2 plus cation. So initially, when I was trying to solve this problem, I initially placed nitrate ion, the sodium cations, and then I figured it out, oh, I made a mistake. because the problem clearly says it is an excess reagent. So then calcium cation is also excess present. I need to put calcium cations also. The answer must be calcium cation. All right. And determine the number of moles of the student filters and dries the precipitate of calcium carbonate, this insoluble solid precipitate, and records the data in the table below. So this is called gravimetric analysis. In a general chemistry laboratory, gravimetric analysis is a very important part. Many times we are going to have a solid precipitate, so we need to filter them. Many times we need to flocculate it. Let's say we need to heat it up, high temperature, let's say 80 degrees, 90 degrees of temperature, 5 minutes of time. We need to make the size of those solid precipitate grow. We call it flocculation. And then we need to use gravimetric filtration, gravity filtration method, and filter those solid precipitate out of the solution. And we are going to put this one in the oven, and we need to dry them in time. And when the mass is reaching a constant mass, we know that this is finally the mass of the solid precipitate. And from this one, we can determine the mass of the solid precipitate formed. Okay, so then in this case, volume of Na2CO3 solution, initial use 50 ml, volume of 1 molarity calcium nitrate solution added 100 ml, and then mass of calcium carbonate precipitate collected after drying in the oven, we found out 0.93 grams. Determine the number of moles of sodium carbonate in the original 50 ml solution. Okay, so then we don't have any other clue. So this is a limiting reactant, and we know that the calcium nitrate is excess amount. Because in excess amount, we cannot determine from the calcium nitrate to find out sodium carbonate. Instead, from this product, calcium carbonate, 0.93 grams of this one, then we go backward. Assuming 100% efficiency, 100% yield of this chemical reaction, then we can determine number of moles of sodium carbonate in the original 50 ml solution. Okay, so then we are given mass. Let's set up a solution map. We are given mass in gram quantity of CaCO3. From here, we can find out mole number, mole of sodium carbonate. Let's use a mole bridge method. So we need to first convert this mole number of mass of calcium carbonate into mole number, mole bridge method, mole of calcium carbonate first. And then using mole-to-mole stoichiometry, you can find mole number of sodium carbonate. So here, let's use molar mass of calcium carbonate. And in the second conversion, let's use stoichiometry. Okay, we are ready now. So let's write the equation. All right. We are given 0.93 grams of calcium carbonate. It is obtained after drying in the oven, reached the constant mass. Now let's convert this one to the mole number. So grams of calcium carbonate denominator and moles of, let me erase it, moles of, let me erase, continue to erase. Okay, so now moles of calcium carbonate. All right, and then what is the molar mass? Here it is given 100.1 grams per mole, and 1 mole of calcium carbonate has 100.1 grams of mass. And in this way, we cancel out grams of calcium carbonate. We were successfully converting the mass to mole number. Now stoichiometry, it is sodium carbonate and calcium carbonate. It is 1-to-1 reaction. So mole of calcium carbonate to mole of sodium carbonate. It is 1 to 1. All right. Then mole of calcium carbonate cancels out. When you calculate it, the value is 0.0093, 0.0093 moles of sodium carbonate. Okay, we find this one. Now let's move up to the next problem. The precipitate was not completely dried, and as a result, the calculated sodium carbonate concentration is too low. Student was realizing and saying, analyzing it like this way. Do you agree with this analysis? No, I don't agree. I don't think so. Let's think about it. So when the precipitate, so we need to reach a constant mass. When you put this one in the oven, what we do is giving them 20 minutes of time, taking it out, making it cool down and measure the mass, put it back, and after 15 minutes, take it out and measure the mass, and then put it back, and after 15 minutes, take it out and measure the mass. We need to see the mass should be reaching in constant mass within certain small difference of mass, allowed mass. Now, a student was asserting that, the precipitate was not completely dried. As a result, the calculated concentration is not too low. All right, so then what it means? So I don't agree. First, this is my, I don't agree. Let me say, if the precipitate, let me write PPT, is not completely dry, dried, then the mass of calcium carbonate is overestimated because it contains water. Overestimated. Then because it is overestimated, meaning according to our solution map, Na2CO3, the amount of Na2CO3 amount is overestimated. Because when you look at the solution map, it is directly proportional. As a result, the molarity of Na2CO3 is also overestimated. Not low, but higher when the precipitate was not completely dried. Okay. Now let's move up to the next one. The filtrate, the liquid that passes through the filter, is tested for electrical conductivity. What will be observed? Here we know that this is sodium carbonate is limiting reactant. We have excess reactant, and we have sodium nitrate is sodium cation and nitrate anion. This one is our spectate ions. So then we already drew those diagrams. When the filtrate, the calcium carbonate was filtered, and in the solution now we have excess amount of calcium cations and nitrate anions. Those are excess amount. And then we have also sodium cations and nitrate anions. They are spectate ions. So then those filtrate contains those ions. So then it will have high concentration of the ions. As a result, the conductivity will be high. Conductivity will be high. Okay. So this one is asking us the interpretation of the diagram. In the diagram we have, in the solution we have excess amount of the cations, anions, and also the spectate ions present. So then the filtrate, the solid will be filtered out, remaining on the filter paper, but the filtrate, the solution contains those ions. Then the solution contains high concentration of the ions. As a result, the conductivity value will be high. Now, A student uses the second method using hydrolysis of carbonate ion. Here I drew the carbonate. So this one is carbonate ion, weak base, carbonate, and it's conjugate acid, bicarbonate ion. And Kb value, look at the Kb value, 2.1 times 10 to the negative 4. Identify a lab method to determine hydroxyl ion. Okay, so let's use a pH meter. So using a pH meter, let's read pH value. Read and determine a pH value. And then from there, we know that pH plus pOH is 14.00. And from there, pOH can be determined when you read the pH value, it is 14 minus pH. Okay, once you determine pOH, then by definition of pOH, hydroxyl ion concentration now 10 to the negative pOH. So by using this method, we can determine hydroxyl ion concentration. So this is anti-logarithmic function. So pOH, every p function is negative logarithmic of the definition. Then when you put anti-log on both sides, then hydroxyl ion is 10 to the negative pOH value. We can determine hydroxyl ion concentration like this way. Explain how to determine the carbonate ion initial concentration. Okay, then we have not used Kb definition yet. Kb is the bicarbonate concentration and hydroxyl ion concentration over the carbonate ion concentration, and it is at equilibrium. Okay, let's set up ice table. Okay, let me draw those bases. Carbonate ion as a base, this one as 2 negative base plus water, and it becomes bicarbonate ion, it's negative 1 charge plus OH negative, then ice. See, initially we have, what is the concentration of carbonate ion? Is it given? No, it is not given, right? So initial, let's say initial, and water will not be appearing. Initially, we have bicarbonate ion hydroxide ion concentration 0. So this one is decreasing, it will be increased by x and x. And it will be initial concentration minus x, and then x and x. Here, look at the Kb value. This is much smaller than 1. Then x will be smaller than initial value. It will be less than 5% of initial value. So then initial minus x can be approximated into initial value. So then Kb is equal to carbonate concentration initial over x squared. Now x is given. We already calculated x like this way. This is x. Hydroxide ion concentration calculated, measured and calculated, and plugging in right there, Kb is given. So we are given Kb, we are given x. So using this equation, let me highlight this equation. When you use this equation, then this is unknown. And then we can calculate K, the carbonate ion concentration. So this one is asking us qualitative analysis of the Kb expression and ice table. Then the Kb value is much smaller than 1, and then it will be typically less than 5% of change. And initial concentration minus x can be approximated many times, most times, to the initial concentration. So then equilibrium concentration now with the given amount approximation, it will be equal to the initial concentration. So we can use the expression of Kb, calculate concentration of Kb. Okay, now let's move up to the next problem. So in the sodium carbonate solution, bicarbonate ion is greater than, less than, or equal to carbonate ion concentration. Look at the value. This one is much smaller than 1. And what is the expression of Kb? Kb is carbonate ion concentration over bicarbonate ion concentration and hydroxide ion concentration. So this was much less than 1. And we already do that this one. This is CO3 2 negative initial under x square. And with the assumption that x is much smaller than initial concentration, CO3 2 negative. In the previous problem, we already assumed this one. CO3 2 negative minus initial minus x is approximately equal to CO3 2 negative initial. We assume this one. This is 5% approximation method. So then it will be HCO3 bicarbonate ion is now much less than the carbonate concentration, usually less than 5%. Usually less than 5%. Okay, 5% of carbonate ion concentration. Okay, that is the sodium carbonate solution suitable for making a buffer with pH of 6. Okay, and then buffer equation, remember, pH can be determined from pKa of the acid plus logarithmic and monopyrrolic acid concentration under its bicarbonate ion concentration. When you write this one in this equation, pH is now pKa value of bicarbonate ion plus and HA is carbonate ion concentration under bicarbonate under carbonate ion concentration. Okay, so this is valid. This is initial. This is the buffer. We need to know the buffer range. Buffer range is, remember, pKa is a constant. So should be pKa value, pH value must be, let me write this one more time. pH value must be within. pH value must be within pKa value plus 1, pKa value minus 1. This is important characteristic. In order to make a effective buffer solution, pH, our desired pH of the buffer must be within 1, range of 1 from the pKa value. Here pKa, here Kb is 2.1 times 10 to negative 4. So when you calculate the pKb, which is negative log of Kb, we see that the value is 3 point something. I calculated this one. Let me see. pK is 3.68. And then pKa of its conjugate acid, which is bicarbonate ion, is 14 minus pKb, which is 3.68. It is now 10.32. Okay, then it is 10.32. Then effective pKa, here let me erase this one. Erase this one here. So erase one more time. Erase. Okay, erase. And then pH value, effective pH must be 10.32 plus 1, 10.32 minus 1, which is approximately 11.3. This one is approximately 9.3. So pH level must be 9, 10 in this range. Then we can use this buffer. When the pH is 6, which is acidic pH, we cannot use this buffer. This is too much away from the pKa value of this bicarbonate ion, so we cannot use this system. as a buffer. No, it is too much away. And this one is very important. Remember, in order to be functioning as a buffer, pKa range, pH range must be very close to pKa value, like Ka, or the ratio of this acid and its conjugate base must be 10 or 1/10 range. All right. So this is asking about the buffer. This is making connection between a precipitation reaction and also another method of concept of buffer, and using is asking us to understand about the Henderson-Hasselbalch equation and its limitation. The buffer range should be within 1 from the pKa value. pH must be within 1 of pKa value, then the system can be functioning as a buffer. If it is too away from this one, then the ratio of the acid and its conjugate base is too large or too small, so then the system cannot be functioning properly. The amount of the concentration of the acid and its conjugate base must be comparable within 10 range. The ratio must be within 10 or 1/10. So then it can be functioning as a suitable and stable buffer. That is a very important concept in the in the concept of buffering capacity. So please remember this relationship, and thank you for watching this video, and I'll see you in next video.